Artificial intelligence is transforming network operations from static automation into intelligent, adaptive systems that learn from data. For decades, we've been automating routine network tasks, but AI introduces something fundamentally different: the ability to understand context, predict outcomes, and act with insight. So let's explore how AI is being applied in network operations today, how it actually works, and what it takes to move from manual workflows to intelligent, data-driven operations. So let's start with the why. Networks are growing more complex more than ever, spanning cloud, data centers, edge, and hybrid infrastructure. The volume of telemetry, events, and logs has exploded beyond human capacity to analyze, at least in real time. Network teams are under pressure to improve mean time to resolution and maintain uptime without expanding headcount. Now, what AI offers is not magic, but a better way to correlate data, forecast performance, and understand network behavior in context. So in short, AI helps operators move from reacting to predicting. Now, historically, we've already used machine learning in networking for capacity planning, anomaly detection, and baselining. Those are proven MLOps use cases. But large language models, or LLMs, are taking things further. So unlike classical ML models, which rely on structured data, LLMs operate on unstructured information, like documentation, configuration files, and tickets, in other words, text. They're built on the transformer architecture using self-attention to understand relationships between words and concepts and even multimodal inputs. And while they're probabilistic, meaning they can produce different answers to the same prompt, their power lies in their ability to synthesize vast information into something usable by humans. So how do we make this useful in network operations? There are several ways that AI is being applied today, and the first is incident triage and summarization. So instead of sifting through hundreds of alerts, an AI system can turn that noise into a single incident summary, highlighting probable root cause and even suggesting next steps. Another application is knowledge retrieval. So think of it as an intelligent assistant that answers how-to questions from your own runbooks, vendor documentation, or KB articles, mapping alarms to known fixes. The next step is automation assistance, generating CLI commands, change plans, or even a full configuration snippet, safely with guardrails in place. And finally, we're seeing advanced traffic analysis where AI explains anomalies from telemetry, identifies capacity issues, and even suggests policy or security adjustments automatically. Now, to make any of this work, you need a solid data foundation. That's where the concept of a data pipeline comes in. About 80% or so of the effort in any AI project is actually data engineering, not model tuning. The pipeline has four main stages: ingest, process, store, and serve. Ingesting means collecting network telemetry like flow data, SNMP metrics, routing tables, logs, and text sources such as tickets or maybe even configuration files. Processing involves cleaning, normalizing, and standardizing that data so it's usable. Then it's stored securely, often in systems designed for both historical and real-time access. And then finally, it's served to models and workflows through APIs. Now, this architecture ensures that AI has accurate, timely information to learn from. Now let's talk about how AI systems actually use that data. One of the most effective patterns is retrieval augmented generation, or RAG. Here's how it works. The user submits a query like, why is traffic spiking on interface gigabit Ethernet 01? The system converts that question into an embedding, mathematical representation, and searches a vector database for semantically related data, such as telemetry, past incidents, or documentation. The LLM then synthesizes an answer using both its general knowledge and that retrieved context. That means the result is an enriched, accurate response grounded in your own data. Another very established capability is text-to-SQL translation. And this allows an engineer to use natural language, like show me the top 5 links by average utilization this week. And the large language model converts that into a SQL query. And then part of a greater workflow executes it against your network data and returns a clear, often visualized answer. It's a great way of democratizing access to data without requiring engineers to memorize complex query syntax. And as these capabilities mature, they're being tied together through agentic workflows, agent systems, systems where an LLM doesn't just respond to prompts, but acts kind of like the brain, coordinating multiple tools. An agent might run traceroute, collect telemetry, consult a knowledge base, and then generate a remediation plan all autonomously, but with human oversight. Now, of course, there are challenges. LLMs are probabilistic, meaning they can hallucinate or provide inconsistent results. So ensuring accuracy and reliability depends on the quality of the training data, proper evaluation, and controlled model behavior. Privacy and regulatory concerns are also critical, especially when handling network data that could contain sensitive information. And then there are, of course, the operational challenges, integrating real-time telemetry, dealing with diverse data types, and managing compute costs for AI workloads. And this brings us to the build versus buy question. Should organizations develop their own infrastructure or adopt vendor solutions? It really depends on goals, resources, and risk tolerance. Building internally offers flexibility, but it requires significant compute, data engineering, and specialized staffing. Buying or partnering with trusted AI-driven platforms accelerates deployment while maintaining security and governance. In many cases, a hybrid approach works best, custom integrations on top of an existing AI observability platform. Ultimately, the goal isn't to replace engineers, but to empower them. AI helps teams move closer to action, automating the tedious data analysis and surfacing insight that leads to faster decisions. It's about designing, operating, and protecting networks with intelligence built in. The network becomes not just programmable, but adaptive, continuously learning and optimizing itself in real time. And as we move forward, the same principles that made TCP/IP and distributed networking so successful, they still apply. Simplicity, scalability, and resilience. AI in network operations represents the next logical step, transforming data into decisions and then decisions into action. By understanding how these technologies work and by applying them responsibly, we can create the intelligent networks our future depends on.